Windows gets all the attention for endpoint security. But here is the reality. Linux servers run the internet. Your bank. Your email. Your favorite websites. Netflix. Every critical service you use daily runs on Linux infrastructure. And when a Linux server gets compromised, the damage is catastrophic. Welcome back to Tech Sky. In our last video, we covered baseline endpoint hardening for Windows 10. You learned the core principles of system hardening, password policies, account lockout, service hardening, advanced logging. Those principles apply to any operating system. If you have a proper guide like the CIS Benchmark and understand these concepts, you can harden any endpoint system according to your requirements. But today, we are taking it deeper. We are moving from endpoint hardening to infrastructure hardening. There is a critical difference. Endpoints are the systems users interact with daily. Infrastructure is the foundation everything else depends on. And right now, our monitoring server, our watchtower, the system that will run Suricata, ELK Stack, and Wazoo, is sitting there with default configurations. No hardening, no advanced logging, no security controls. Think about what that means. If an attacker compromises our monitoring infrastructure, they can delete all security logs, disable monitoring across the entire network, plant backdoors in our defensive tools, and pivot to every endpoint we are trying to protect. We would be completely blind while they operate freely. That is why infrastructure hardening is more critical than endpoint hardening. A compromised endpoint affects one user. A compromised monitoring server affects your entire security operation. And today, we are securing it with industry-standard controls. Advanced system auditing with Auditd. Network perimeter defense with UFW. Automated threat response with Fail2Ban. Cryptographic authentication with SSH Hardening. By the end, this server will be locked down with production-grade security controls. Let's begin. Open your web browser and navigate to the CIS website. We already have an account from week 4, so log into the portal. Click on CIS Benchmarks. Scroll down until you find the Ubuntu Linux section. Expand it. We need the PDF matching our Ubuntu version. Our lab uses Ubuntu Server 22.04, so download that benchmark. This CIS benchmark covers both Ubuntu Server and Ubuntu Desktop, so the same PDF applies regardless of which system you are hardening. Move it to your desktop and open it. This looks similar to the Windows benchmark, but the approach is different. In week 4, we started with basic hardening and built up to advanced logging. This week, we start with advanced logging and build security layers on top. Scroll through the table of contents. System logging, access control, network configuration, services. Keep this open for reference. Open VirtualBox. First, start pfSense so our VMs have internet access. Wait for it to boot completely. We have 2 Ubuntu machines, Ubuntu Server and Ubuntu Desktop. Start Ubuntu Server. After it boots, open a terminal on your host machine and SSH into the server. This is how you would manage production servers in real environments. First, make sure the system is updated. Run sudo apt update, then sudo apt upgrade. My system is already updated. Now we install Auditd for advanced system auditing. This is where our approach differs significantly from week 4. Instead of building up to logging, we are starting with comprehensive logging and then layering other security controls on top of that foundation. Type sudo apt install Auditd and let it install. Once that completes, we need to start the service and enable it to run automatically on boot. Type sudo systemctl, start Auditd to start it now, then sudo systemctl enable Auditd to make it permanent. Check the status with sudo systemctl status Auditd, and you can see it is active and running. Now comes the important part. Configuring audit rules based on CIS benchmarks. Type sudo nano/etc/audit/rules.d/CIS hardening.rules to create a new rules file specifically for our hardening configuration. Switch to the CIS PDF and find section 6.2.3.1 in the table of contents. Open it up. We are starting here instead of at the beginning, because this video focuses on advanced configuration rather than walking through every single baseline setting. You should read through the benchmark yourself and implement the settings that make sense for your specific environment. At the top of the page, you will notice this section shows Level 2 recommendations for both server and workstation. We discussed CIS levels in our previous lab. The important thing here is that these security configurations apply to both Ubuntu Server and Ubuntu Desktop, which the benchmark calls Workstation. The same hardening principles work across both system types. Copy the recommended rules from this section and paste them into your rules file. These rules monitor any changes to sudo configuration files. The first rule watches /etc/sudowars for write and attribute changes, and tags everything with the key scope. The second rule does the same for the /etc/sudowars.d directory. These are critical because attackers frequently try to modify sudo permissions as a way to escalate their privileges on compromised systems. Next, we add rules that monitor any attempts to change system time. You might wonder why time changes matter for security. Attackers often modify system time to cover their tracks in logs, or to bypass time-based authentication mechanisms. These rules monitor system calls like adjtimex, set time of day, and clock_set time for both 64-bit and 32-bit architectures. They also watch the /etc/localtime file for any direct modifications. Now for system locale and network configuration monitoring. These track hostname changes, domain name changes, and modifications to network configuration files. All of this gets tagged with the system locale key, so you can easily search for these specific events later. The next set covers identity management. These are some of the most critical rules, because they watch all your authentication files and configuration. Any changes to these files could indicate account manipulation attempts or privilege escalation in progress. The final set monitors login and logout activity. These rules watch the last log and faillock directories, capturing both successful and failed login attempts. This is essential for detecting brute force attacks and unauthorized access attempts. Save the file and exit nano. Now we need to load all these rules into the kernel. Type sudo augenrules-load, and this compiles all your rule files and activates them immediately. Let's verify everything loaded correctly. Type sudo audit ctl-l pipe head-20 to see the first 20 rules. You can see all the rules we just configured are now actively monitoring your system. Time to test this and make sure Auditd is actually capturing events. Type sudo user add test user to create a new user account. This action modifies both /etc/passwd and /etc/shadow, so our identity rules should capture it. Search the audit logs by typing sudo au search-k identity pipetail-1. This searches for events tagged with that identity key and shows you the most recent one. Look at this detailed audit record. You can see the syscall type, the exact timestamp when it happened, the process that made the change, which is user add, the full path to the executable that ran, the process ID, the user ID who executed it, and right at the end, you see key equals identity confirming our audit rule caught this event. This is the raw forensic data that investigators use to reconstruct exactly what happened on a system. Now type sudo au report-summary to see an overview of all audit activity on the system. This generates a complete summary report showing login events, file modifications, system calls, authentication attempts, everything audit has been capturing since we activated it. This level of visibility is what makes real forensics and threat hunting possible in enterprise environments. Next up is UFW, the uncomplicated firewall. This is a host-based firewall that protects this individual server, different from pfSense, which sits at your network perimeter protecting everything behind it. This is defense in depth. Network firewall plus host firewall. Type which UFW to check if it is already installed. You can see it is there by default on most Ubuntu systems. If for some reason it was not installed, you would just type sudo apt install UFW. We are going to configure this firewall according to CIS recommendations, which means starting with a secure default deny posture. Type sudo UFW default deny incoming to block all incoming traffic by default. Then sudo UFW default allow outgoing, so the system can still make outbound connections for updates and normal operations. Finally, sudo UFW default deny routed, because this server is not acting as a router. Now here is the critical step. We need to explicitly allow SSH before we enable the firewall, otherwise we will lock ourselves out of our own server. Type sudo UFW, allow 22/TCP, comment SSH. That comment at the end documents why this rule exists, which is helpful when you are reviewing firewall configurations months later. Before we enable this firewall, let's review what we just configured. Type sudo UFW show added, and you can see the SSH rule we just created. Everything looks correct. Enable the firewall by typing sudo UFW enable. It will ask for confirmation, because it is warning you about potential connection disruption. Confirm it, and the firewall activates immediately. Check the status with sudo UFW status verbose, and you can see the firewall is now actively protecting your system. Let's prove this is actually working. Try connecting to a port that should be blocked. Type timeout 3, telnet localhost 80, and watch what happens. It times out after 3 seconds, because port 80 is blocked by our default deny policy. Now try an allowed port with the same command, but using port 22. And this connects immediately, because we explicitly allowed SSH traffic. Your firewall is now protecting the host from unwanted network access, while still allowing the legitimate services you need. Now we add another layer of defense with Fail2Ban for automated brute force protection. This is an intrusion prevention system that monitors log files and automatically bans IP addresses showing malicious behavior. UFW gives us the firewall rules, but Fail2Ban makes those rules intelligent. No manual intervention needed. The attack stops itself. Type sudo apt install Fail2Ban to install it. After installation completes, we need to start and enable the service. Type sudo systemctl start Fail2Ban to start it now, then run the same command, but change start to enable for automatic startup, and finally change enable to status to verify it is running. Now we configure custom jail settings. In this context, a jail is a monitoring profile for a specific service. Each jail defines what to watch, what patterns indicate attacks, and how to respond. Type sudo nano/etc/fail2ban/jail.local to create a local configuration file that overrides the defaults. I am providing this complete configuration in the CDM repository, but let me explain what each setting does. Under the default section, ban time is set to 600 seconds, which means 10 minutes. That is how long an IP address stays banned. Find time is also 600 seconds, which defines the time window for counting failures. Max retry is 5 attempts before triggering a ban. Banaction defines what action gets taken when an attack is detected. We set this to UFW, so the system will automatically add block rules to the firewall we just configured. Under the SSHD jail section, we enable protection specifically for SSH. Tell it to monitor /var/log/auth.log for failed login attempts, and ban any IP that fails 5 times within our time window. Save that file and exit. Restart the service with sudo systemctl restart Fail2Ban, so it picks up the new configuration. Check which jails are active by typing sudo fail2ban-client status. You can see the SSHD jail is running. Get more details by adding SSHD to the same command, and it shows 0 banned IPs right now, because no attacks have occurred yet. Let's simulate an attack and watch the automated response. I am providing this command in the repository because it is long, but what it does is inject 5 fake failed SSH login attempts into the auth log file, exactly like what would appear during a real brute force attack. After running that command, wait about 5 seconds for log processing. Run the status command again, and look at this. You now see one banned IP address. The system detected the attack pattern automatically and blocked the attacker through UFW without any manual intervention. You can unban everything for testing purposes by typing sudo fail2ban client unban all, but in a production environment, you would leave those bans active to keep the attackers locked out. Your server is now defending itself automatically against brute force attacks in real time. This is our final hardening layer. We are securing SSH for remote access. SSH is how administrators connect to servers remotely, so hardening this service is critical. We will implement key-based authentication, disable password logins, and configure strict access controls. Start by backing up your configuration. Type sudo cp/etc/ssh/sshd_config, then type the same path again, but append .backup at the end. Verify the backup with ls-lh, and the same config path with an asterisk. You can see both the original and backup file. Always create backups before modifying critical configuration files. Now we set up key-based authentication, which is dramatically more secure than password authentication. Open a new PowerShell terminal on your Windows host machine. Type ssh-keygen-t-ed-25519-c defender at Ubuntu-server to generate a new key pair. This is a modern, cryptographically secure key type that is faster and more secure than older RSA keys. Accept the default file location when prompted, and you can optionally add a passphrase for extra security on the private key. Display your public key by typing type, followed by the key file path in the .ssh directory. The entire key appears on screen. Copy that complete line to your clipboard. Switch back to your Ubuntu server terminal. Create the SSH directory, if it does not exist yet, by typing makedir-p_/.ssh. Now set the correct permissions with chmod 700, followed by that directory path. This permission setting is absolutely critical, because the service refuses to work if the directory permissions are not secure. Create the authorized keys file with nano-ssh/authorized_keys and paste your public key into this file. Save it and exit. Set the file permissions with chmod 600 on that file. These strict permissions are required for the service to trust the file. Verify everything is in place with cat to view it. You can see your key sitting there ready to use. Before we disable password authentication completely, let's make absolutely sure key-based authentication is working. Type exit to close your current connection. Now reconnect to the server. Watch what happens. You connect immediately without being prompted for a password. The service is using your cryptographic key pair for authentication instead of passwords. Now we lock down the daemon configuration itself. Type sudo nano/etc/ssh/sshd_config to open the main configuration file. Scroll down and locate log level. Uncomment and set it to info. This ensures detailed logging about every connection attempt. Next is login grace time. Uncomment and set the value to 60. This automatically disconnects any connection that sits idle at the login prompt for more than 60 seconds. Moving to permit root login. Uncomment and set it to no. This prevents anyone from logging in directly as root, which is a major security improvement, forcing administrators to use regular accounts with sudo. Max auth tries comes next. Uncomment and set it to 4. This limits how many password attempts someone can make before getting disconnected. You will see max sessions below. Uncomment it, and you can see it is already set to 10, which is a reasonable limit on concurrent sessions. Further down is permit empty passwords. Uncomment and verify it is set to no. This prevents any accounts without passwords from logging in. Continue to client a live interval. Uncomment and set it to 15. Right below that is client alive count max. Uncomment it and you can see it is already set to 3. Together, these settings mean the service will check if the client is still alive every 15 seconds, and after 3 failed checks, it automatically disconnects inactive sessions. That is 45 seconds of inactivity before disconnect. These settings all come from CIS recommendations. But understand something important here. You do not have to blindly follow every recommendation. CIS provides a security baseline that works for most environments, but your specific situation might require different settings based on your risk tolerance and operational requirements. Save the main configuration file and exit. Now open the cloud-init configuration with sudo nano/etc/ssh/config.d/50-cloud-init.conf. Set password authentication to no. This completely disables password authentication across the entire service, requiring everyone to use cryptographic keys instead. Save that file and exit. Test your configuration for any syntax errors by typing sudo sshd-t. If there are no errors, nothing appears, and you just get your prompt back. That means the configuration is valid. Restart the service with sudo systemctl restart sshd to activate all the changes we just made. Check that it restarted successfully by changing restart to status, and you can see the service is running with your new secure configuration. Time for the final test to make sure everything is working as intended. Type exit to close your current session completely. Now try connecting without using your key by typing ssh-o pubkey, authentication equals no, followed by your username and server IP. Watch what happens. Permission denied. The server completely rejects the connection because password authentication is disabled. Only cryptographic key authentication works now. Try connecting normally without any special options. It connects instantly using your key pair. This is the perfect combination of security and convenience. No passwords to remember, no passwords to crack, no brute force attacks possible. Just cryptographic authentication that works seamlessly. Your Ubuntu server is now hardened with enterprise-grade security controls. Look at what you just accomplished. This is not a default installation anymore. This is production-grade infrastructure security. The same controls protecting enterprise data centers and cloud infrastructure. Save your work by taking a snapshot. If you found this video helpful, hit the like button and subscribe to the channel for more powerful content. Share it with your friends, colleagues, or anyone who might benefit. And if you think something could be better, tell me in the comments. Your honest feedback helps me improve and bring you even better content next time. This is Tech Sky. Stay curious, stay ethical, and keep learning.